So yeah, I was asked to give a lecture on high energy physics methods in condensed matter. And I think the first thing I found out is there's no such a thing. So there's just methods. And people use them all over the place. And so I think the first, if you have to take just one thing out of this, is that the first thing is that you have to, be brave and open all kinds of books. Don't let the labels, prevent you from opening this paper or this book, because, you just have to find a dictionary, and once you find a dictionary, it's all there. And I think the best physicists knew everything. So I hope this lecture, even if you don't get all the details, will kind of empower you to dive into high energy literature from condensed matter, and maybe put your own creative mind there, and also bring stuff from there, so that we don't rediscover things all the time, which is what typically happens. Okay, so instead of methods, it's basically a collection of warnings and facts and some ideas that you might encounter in your life while studying essentially vial and gapless states of matter, that I'm going to rephrase as Lorentz breaking theories, actually, from high energy physics. And in fact, Lorentz breaking, despite common knowledge, has been quite studied in high energy physics, because people like to think about beyond the standard model, and of course they need something to do. So and in fact, they're quite interesting, because Lorentz symmetry is a very restricted symmetry. So what happens is that it prevents a lot of ambiguities in theories, in fact. And so we're going to encounter some examples of those ambiguities. And for us, they're pretty important, because they lead to observable quantities. So how do we fix them, and what does this mean for, like, in the high energy perspective? How does this translate to the condensed matter, etc.? That's going to be pretty much point 2. So just a word of warning: I'm not going to be like extremely detailed, because it's impossible to give like a quantum field theory course in like 3 hours. But so it's going to be more plausibility arguments rather than like technical derivations. And also, I want to like a show of hands of how many of you have been exposed to quantum field theory or high energy physics before? Okay, that's okay. So maybe you should be giving the lecture. Fantastic. Okay, good. So I was gonna say, I was expecting less hands. So I'm gonna start with a. Can I erase this now? Okay. I was gonna start with a. Let's see. How many of you can diagonalize a 4x4 Hamiltonian? Good question. Let's say with a computer. Okay, I hope everybody raised their hands. So I'm going to write a 4x4 Hamiltonian, and whenever you're lost, look at this Hamiltonian and you'll be fine. Okay, so this is obviously a blackboard that bounces. So I'm going to write a lot of things here, so I'll explain this in a lot of detail in what follows. So don't worry too much right now. Okay, 4x4 Hamiltonian. What are these things? So one important thing here, sigma are the Pauli matrices 2x2, real spin. Okay. K, we're 3 dimensions. Like you can assume we're always going to be 3 plus 1 is what people say in high energy. It's like time too. So this is the momentum. I'm going to take it as a continuous variable, and at some point we will make connection to the lattice. So this is kind of the opposite approach to all the lectures you've seen. We're kind of going from the low energy to the lattice rather than from the lattice to low energy, or that's what we're doing. So now it's convenient to define. So you notice I have a vector B that has 3 components and a scalar B0. Yeah. Okay, you'll see what I mean. But what I mean is that at some point we will write a field theory, and then we will kind of lattice it. That's what I mean by latticization. I don't know if this word exists, that's why it's on quotes. But there's, like, if you write a field theory, there's, like, easy ways to just write a theory that's periodic. Yeah, we'll go through that. Okay. So, yeah, so we have a 3-vector here, a scalar here. High energy physicists like 4 vectors, so we're going to write a 4-vector in this way. So mu is an index that goes from 0 to 3, and then I use Greek indices to denote 0 to 3, so 0 is usually time. And then Latin indices to go from 1 to 3. So just spatial indices would be Latin letters. That's a common convention. And some things that you will encounter in high energy papers is that when you define this product, it's not exactly the vector product. It has some structure to it. In particular, you just have to put a minus sign to the spatial part. So I defined a signature of the metric, if you want to call it that way. I'm going to call M the mass. And this is not going to be equivalent to a gap, by the way. These are going to be 2 different things. And so, yeah, so this is my Hamiltonian, and I'm going to show that this Hamiltonian is actually like with this Hamiltonian, you can understand pretty much 90% of the papers in vial semimetals that do not involve superconductivity, but well, maybe like then you can generalize it and double it and so on and understand maybe 99%. And then I'm going to discuss some generalizations that will allow us to describe nodal lines and stuff like that. Okay, so right, so this space, this Hamiltonian acts in in a 4x4 space with real spin. The other degree of freedom I'm going to leave open. It depends on the system. I'm not going to say too much about it, but this Hamiltonian is going to act on a kind of wave function that I'm going to write as in K space. I'm going to write as so it's a 4-component wave function, and I'm going to write it as two component objects. Actually, I should write, to be precise here, this guy. The other one is just a vector. And so the first thing, before I go into like the details of what's the spectrum and so on, which you could already probably guess, I'll define some notation. So one thing that, so let's say, so I can write it in a kind of compact manner, this Hamiltonian in the following way. So I'm just going to write some matrices that I would like to use. So these big gammas are just matrices that I'll define. But I mean, you can see the definition from there, actually. But okay, so in particular, gamma 0, for example, is just sigma 0 cross tau 1. So this is Kronecker product. Multiplies the mass, so it's kind of here. So you have to imagine that there's a big 2x2 one here. Okay, so far so good. And likewise, you can define the other matrices. Gamma I is just sigma I cross tau 3. Gamma 5 is just sigma 0 cross tau 3. By the way, I will provide lectures, so lecture notes, so feel free to just listen. Gamma IB can be written as cross tau 0, and so on. So so this is one way to write the Hamiltonian in a easy notation. One thing that you will encounter too in high energy is that instead of defining this object, people like to define something that is called a Dirac joint for reasons that involve Lorentz invariance, actually, which is just simply this guy. So it's just you multiply this guy by your gamma 0 and you're done. And now there is also the need, or I don't know, it's a matter of choice, but it's easy to go from the Hamiltonian language to the Lagrangian language, and I'll be using or the action language, and I'll be using that a lot. So I'm gonna rewrite this guy as an action right now. So okay, so this Hamiltonian is actually depends on k. It's an operator. I can define Hamiltonian density in 3D. Let's say so schematically something like this. And now what I want to do is define the Lagrangian as essentially like Lagrangian density somehow as omega minus h of k. And what I want to do is I want to write in a funny way. I want to, since most of the high energy literature is written like this, I'm going to connect to this by just using the fact that this matrix squared is just the identity. So I just write that. So I can write, I can multiply this guy by the identity, no problem. So I'm going to use one of them to put it right here, the other one to put it right here. And I can define now this guy, which is I'm going to call the action. And now this is just what I call the Dirac joint. And now I can try to see what the hell is this object. Yeah, omega is PQ. What do you mean PQ? So omega is just the frequency. It's just the zero. So if I write a 4 vector, which I will write now, it's just like the energy. It's just the energy. I could call it E if you want. I'm just writing a generalized momentum incorporating the energy and the K. So BE. Like from doing derivatives of this action will give you like the Schrodinger equation essentially. But okay, so so now I can use this compact notation to write this in a kind of neater way. So what this gamma 0 is going to do is it's going to redefine all my big like capital gammas here. That's just what it's going to do. So the redefinition, like basically gamma 0 and these guys are basically we call them the Dirac matrices, and they're represented by some small gamma. So there are 4 of them, and I can define also gamma 5, which actually you can check that it's the same as the big gamma 5, and gamma 0 is actually the same as gamma 0. So I can rewrite this action in a more compact way using this 4 product here. And I guess I can leave it as an exercise, but if you cannot do it, you can ask me. So whoops. So in a way, I wrote the Schrodinger equation. Basically, you can imagine like writing the Schrodinger equation here, and the E now, instead of going with the identity, goes with this gamma 0 because I did this trick. So I can write it in a very compact way by contracting with this gamma mu's that are just gamma 0s times the other matrices. And so you can check that, well, the mass goes with gamma 0, so it now goes with the identity and so on. And so I can write this term, which is going to be very important. So I'm going to write this theory here because we will use it a lot. So, okay, I think you can remember that K is the momentum, so I'm going to erase that. So just remember, this is exactly the same theory as this one. So if you're lost in that notation, just remember that this thing is the same. So it's just a matter of writing somehow in a compact way things. Okay. Very good. And so one important thing, let's see. One important thing that this gamma 5 matrix is actually quite important. You can also check that it's a product of all other gamma matrices. Like gamma, so it's basically gamma 0 times gamma 1, gamma 2, gamma 3. And it's, well, some people put an I, but that's fine. So it's a product of all gamma matrices. And since it's a product, actually, it anti-commutes with all of them. So this is important, an important property. So I'm going to put this here. Gamma 0, okay. And now, okay, so I introduced a bunch of notation, but now let's see what we can do with this theory, because this theory actually can interpolate from an insulator to a Dirac semi-metal to a vial semi-metal, depending on the value of all these parameters. So I'm going to show that. And that's pretty powerful, because then you can understand how a vial semi-metal responds to an electromagnetic field by coupling this to an electromagnetic field. You can understand arcs by making this parameters vary in space. So there's a lot that you can do with this simple Hamiltonian, or the simple action. Some of the things I mentioned I'm not going to do, but just to say that this is quite powerful. Okay, so I'm going to erase this. So questions so far? You please interrupt me, of course. Okay. So, right. So the Schrodinger equation now looks a bit funny, but it's just means it's the same. So basically, you can write it as something like this. And so you can solve for, there's an E here, so you can solve for eigenvalues. And okay, it's a 4x4 matrix, so it has 4 bands. So let's try to find some easy limits and give them some names. So Dirac. I'm going to call it massive Dirac because. So I'm going to set all components of this 4 vector to 0, and I'm going to choose the mass to be non-zero. So that, what does this give? That just gives this, right? So what is this? This is just a Dirac, massive Dirac Hamiltonian, right? We know how the spectrum looks. It's just 2 bands. And you can notice that I haven't put like Fermi velocities or anything like that. I'll do that later, but let's just focus on this first. Right, so this case is just very simple. It's 2 degenerate bands with a gap that 2m. So these are doubly degenerate. So they're fall on top of each other. Okay. Doesn't matter which K I plot because it's isotropic. Okay, so this is what we would call in condensed matter an insulator. So that's good. So this Hamiltonian has an insulator in it when M is non-zero and B is 0. Okay, now we can look at another limit. So call a Vial limit. So in this context, I'm using Vial as in the high energy, but in the high, like in the condensed matter community, I guess this would be called a Dirac semi-metal. But it's it's a Vial. It's actually the Vial equation or Hamiltonian in high energy physics. So on that. So this, you can already guess, it's making m equals 0, b mu is 0. So all I'm left with is this diagonal block. So plus minus. Right. So now we notice, of course, that this Hamiltonian is very symmetric because it's block diagonal. And we call that symmetry the Chiral symmetry. But this is not the Chiral symmetry that we've been hearing about. It's a different symmetry, just to make things even more confusing. I guess one reason, if you just want one reason why this symmetry is different, is that this is a continuous symmetry, while the symmetries that have been introduced as Chiral symmetry are discrete. So this symmetry says the following thing. It's a transformation, obviously. And it looks a lot like a gauge transformation where you would add a phase to this spinner, but actually it comes with a gamma 5 matrix. So this is a parameter that I use to describe the symmetry. And it comes with a gamma 5 on top. And in fact, the psi bar has the following transformation. So this is true because, so you notice that there's no minus here. And the reason is the gamma 0, that it will have a minus, but then once I commute with the gamma 0, it kills the minus. Okay, so now I can ask, what happens if I have this Lagrangian, and I ask whether is it invariant? Okay, we set the b to 0. Is it invariant to this symmetry? Does it stay the same when I apply this? So let's do it. Now, the first term, the k doesn't care, so I can write I theta halves gamma 5 k mu gamma mu. Okay, so this is the transformed one. Now, if I look at the first term, the gamma 5, I told you anti-commutes with this guy, so it's going to acquire a minus sign, and it's going to kill this guy. So this term is okay. So this term is invariant under that symmetry. But this guy has no gamma 5, so it's actually not invariant. So this m breaks Chiral symmetry. So what this m is doing is actually coupling the two Chiral Hamiltonians, which are this diagonal part. And so if m is 0, we can define the eigenstates of this gamma 5 will be also the eigenstates that diagonalize this guys. So I'm going to define those, I guess, here. And of course, I already erased it, but I told you that I was working I already called them anticipating this fact. I chose a basis where this fact is really apparent. This is called the Chiral basis for this reason. And so I can define simply by inspection that I can transform a Dirac spinner into a Vial spinner. Yeah. Yeah, so m is not 0 in this, from this part of the line. So to the right side of the line is m is 0. Well, okay, not here, but but okay, so
you put b to 0 here, right?
b to 0, yeah. B is always 0 so far. Yeah. Sorry. So I just wanted to say that m was not invariant under this transformation. So that's why I make it 0, so that I can define this guys. Because now, so we say that this two 2x2 wave functions have a definite chirality because they're eigenstates of gamma 5. And these guys are called the projectors. So this object here projects the 4x4 spinner into something that's 4x4, but it only has either right or left. Okay. So in fact, I mean, this is quite easy to see because in this basis, gamma 5 is just -1, 1. So once I add the identity, I just select one of the two components of this 4x4 object. And when I say 1 by 1, I mean something like this. Okay. So so now we define chirality as eigenstates of gamma 5, essentially. One side note is that you might hear, yeah.
Why do you have to define chirality as a continuous parameter? Why don't you just call it gamma 5?
Oh, but this is just how you implement symmetries. You choose a parameter.
You can implement it as discrete as well, right? Why make it
Is there a why in life? I don't know. I think there's a how, but a why. I don't know. So sigma what?
Just multiply by gamma 5.
Oh, just you want to do like this to gamma 5? Sure. Yeah. But okay, I guess the reason I do this, okay, besides from all the historical background and so on, yeah. So this parameter is actually, or changes in this parameter would actually mean something at some point. I'm not sure. I don't think I'll cover that. But in fact, well, okay. Let's say this has some physical information to it, just like when you do just a normal U1 transformation in a theory, and you impose conservation of that charge, you would find like your laws of conservation of charge. So this continuous symmetry, by Noether's theorem, has also some implications in terms of conserved currents, and so it's important to allow that, because if not, you would be missing all that information, I guess. Okay. So yeah. So I was going to say that you might have heard that there's something called helicity as well. So helicity and chirality are not the same thing. They're just the same thing in the massless limit. Okay. So this kind of completely outside. So I can put in a box, and I'm not going to go into that. But helicity is defined. So H, small h, is defined as actually a 2x2 matrix. So that's already a difference. P is momentum. And it's the projection of the spin along the momentum component. And this itself changes under Lorentz transformation. So it's actually like if an observer can see a different orientation of the spin depending on the reference frame, unless that particle is going at the speed of light, which means it's massless. So, but this is just a side note, just to because this is sometimes confused even in books. So I kind of want you to know that there is a difference. But okay, so helicity equals chirality only if m is 0. Basically, so if mass is non-zero, you can write this guys as a superposition of states with defined helicity. That's what I mean. Okay, so after this side note, so now I'll talk a bit about, so I talked already a bit about symmetry here. But okay, let's see. So I guess I can erase the outline here. Now, if I think, one would say, okay, I like this Hamiltonian to describe vial semimetals because this is gapless, it has a spectrum like this. You know, it has like the two Hamiltonians kind of fall on top of each other. I like this. Why don't I use this? Okay, so this is Dirac semi-metal. And the reason I don't want to use this to describe Vial is because these two copies actually can talk, and they can talk through the mass term, as I said. And the reason this is not protected is because the mass term doesn't break any discrete symmetry, like time reversal, for example. So if you take the time reversal operator that has been defined many times, and you, well, I can actually write it like this. In this case, it would be this guy. And you apply it to this thing, you would see that the mass doesn't break any of that. And it doesn't break inversion either. So in principle, it's allowed by discrete symmetries. So, and chiral symmetry is not, it doesn't really have to be preserved in nature, and even less in crystals. So sorry, it doesn't have to be preserved at this level. Forget about the crystal. And so now it means that there's nothing that protects me to add a mass term. So in fact, these two guys can actually talk. So I want to do something that makes them more stable. And this is the role of this vector B. So this is going to separate them in momentum space. And here's where we're going to break Lorentz invariance, actually. Okay, so 3. I don't have a good name for this one, so I'm just going to say the parameters. M equals 0, but then I'm going to choose a space like B, which just means that I choose the time component 0 on some B. So this is completely space-like. Okay, so now how does the spectrum look? So the Hamiltonian is just K minus B sigma minus K plus B sigma, right? Right. So what I'm doing is I'm shifting the two chiralities by a vector B. So my spectrum just looks like this, where this separation. So this is energy. This is Kz. Or yeah, I guess I chose them. Let's say I choose this to be 0, 0, Bz. So this would be 2Bz. Okay, so I'm separating the two vials in momentum space. And so now you can ask, so I'm going to call the vial node separation this. In general, it would be this. So delta of big K. So now you can ask, isn't this now better? And in fact, it is, because even if I add a small mass here, let's say I add a small mass. And by small, I'll define what I mean by small in a second. Like by now, let's just choose it way less than B squared. What do you think this guy is going to do? Is it going to open up a gap here or something, or is it going to do something else? Sorry? Moving K? No, because moving K would mean to change. Well, they would move. Okay, so yeah, okay, but actually the most drastic feature is actually that there's a small hybridization of these of this bands. And the reason I said yes, that they move in K, is because now if you compute the distance, it would be something that looks like this: 1 minus m squared b squared. So you see this theory, if m is small, this is great because it opens up a gap, it moves them a bit closer. But if m, if B becomes larger than m, this kind of becomes imaginary. So smaller than m, then becomes imaginary. So then how can a momentum space separation be imaginary? And And what happens is basically that at that point, you open up a gap. And so the vial node separation doesn't make sense anymore. And so this theory knows about all this. And now we are in position to know how the spectrum evolves as a function of parameters. So you can actually play with this very easily in Mathematica. But so now what happens is, I can start with B non-zero, spatial B, m equals 0, and I have this. Now I start increasing m, and whoops, I get this. And at some point, and this guys just move towards each other. So this is m smaller than b squared. And now at some point, actually when m squared equals b squared, the vial nodes annihilate. So this is kind of the only way I can gap out a vial system, just by annihilating the two nodes. The reason is that they're, as we heard from Ivo, they're monopoles in momentum space. So you can only annihilate them by pairs. And then as I increase m further, I'll just have this guy. And finally, if b is 0 and m is non-zero, I'll go back to the Dirac spectrum. So this guy can interpolate all the way from a vial semi-metal separated hybridized band to an insulator. And if both m and b are 0, then you have what you would call a Dirac semi-metal. So this is a Dirac semi-metal. Say ideal vial, and anything in between. With that simple Hamiltonian, 4x4. And the good news is that this has been studied, like we've connected to this Hamiltonian to some theory that has been studied in other contexts. So we can borrow many of the results and actually find interesting things. I think that would be my next lecture. But now I haven't mentioned this B0 yet. So B0, if I look just at one of these blocks, B0 is just goes with the identity. So this, actually I might call it sigma 0 or something. So sigma 0 and 1, like the identity in 2x2 is the same thing. So this actually enters like a chemical potential, but unlike the chemical potential, it enters with different signs at different nodes. So there's a minus sign here. So then what this does is generically shifts the nodes up and down in energy. So for finite, so when B0 is non-zero, if I take this situation, well, let's take this situation. Just to exaggerate a lot, I'm going to have something like this. This is going to be proportional to B0, and this is going to be proportional to the B. So I'm going to separate them in energy space by B0, and in momentum space by B. Now, how do I know, which values the parameters give me what? So here's the rule. The vial node separation in energy and momentum space, so that's what this mu means. 0 means energy space, 1, 2, and 3 means momentum space, is the following object. 2 times b mu, 1 minus m squared b squared. Okay? So this, as long as this, let me, where is this? is, I'm going to define as b squared is bigger than m squared. This is gapless. It's gapped. Okay, so this is the condition. So this b squared now is the 4 vector squared. So this is this object. So it includes b0. Which means that, in particular, if I only have b0, the system is always gapped, because we are always in this case. You can check that explicitly. So, for example, so if I take space B 0, M non-zero, but B0 non-zero, the band's going to look like this, which in fact looks a lot, if you look at the tellurium, there actually, it looks like this. And here's your vial, and here's your vial, and this is the vial node separation. Spectrum is gapped, but there's some vials here. Unless I dope it, I cannot access them. Okay? So I think this is a pretty awesome model. I made a career out of this. That doesn't mean much, but it's important to me, I guess. So now let's talk about a bit more about symmetries of this object, the B and the B0, which is what I'm left with. Okay, so I'm gonna do it here. Symmetries. I consider the spectrum. I'll consider symmetries. Okay, so 1. This object. How does it behave under time reversal symmetry? Like, if I include this, is this Hamiltonian time reversal invariant or time reversal breaking? And you don't have to do any calculation to see this, actually. So how does it couple? Like, eliminate everything. How does it couple? Couples like this, right? You've seen this coupling before. It was in Ivo's lecture. This is like a magnetic field. In fact, it's like a magnetization because it's an intrinsic property of the system. So B actually breaks time reversal, but preserves inversion. So adding B, meaning breaks time reversal symmetry, preserves I. As I said, not many calculations. It's all hand wavy. But you can explicitly check this, obviously. Now, B0, how does it couple? Well, it couples with the identity matrix, so that's like a chemical potential. So what does a chemical potential break? It definitely preserves time reversal symmetry, but it breaks inversion in this simple model. So meaning when I separate the vial, so core message, like when I separate the vial nodes in energy, I'm breaking inversion in this model. When I separate them in momentum space, I'm breaking time reversal. If I do both, I break both. So this term, so this part of the Hamiltonian preserves time reversal symmetry and inversion, and with this term, I'm breaking both of these. Now, Lorentz symmetry, finally. I mean, I'm assuming you've all been exposed to, at some point in your undergrad, to Lorentz invariance. So I'm just going to appeal to that knowledge, and a very basic one. So Lorentz symmetry relies on kind of invariance under frame transformations. And this B mu is a vector in space-time. It points there. So it's a preferred orientation. So you already have to, like, at least intuitively agree with me that this looks like a Lorentz breaking term. In fact, it's a bit more subtle, because what we don't learn in undergrad is that you can define two types of Lorentz transformations. When they're called observer particle transformations, which is what you all kind of have intuitive in your mind. You change coordinates and your equations of motion kind of look the same in this new coordinate frame. And then you can define particle transformation, which in fact have an extra addition to that, which is I transform everything, but some things remain unchanged. And so I'm going to illustrate this with a simple example. And so let's say you have a box, and you have a particle in this box, and there's some gravitational field, for example. And now I'm going to, so this is my box. I'm going to draw it here like dashed because I want to do something to it. Now, so rotations are part of the Lorentz group. So I can rotate the box. But if I don't rotate the Earth, I don't preserve my equations, right? Because G would still be going this way. So what I did here is a particle trend. It's a particle rotation. So I'm leaving G invariant, and this chooses a preferred direction. So this is what B does. So in this example, I can rotate the Earth. But if B is a property of my vacuum, a magnetization, so it's a spontaneous breaking of some symmetry, then I'm not allowed to rotate it, actually. So it actually prefers, so magnetizations break Lorentz invariance because they point somewhere. So if this force that I'm drawing here comes from the vacuum, then like from the actual state that I'm trying to describe, then I'm not allowed to rotate it. But in fact, this theory does preserve the fact that, if you kind of rotate everything, then it's obviously going to remain invariant. But if I don't rotate B, that B, which is G in my example, then I'm going to break it. So that's the way this B breaks Lorentz invariance. So basically I'm just assuming that this B is going to remain fixed once I do the Lorentz transformation. It's kind of like when you when you have a particle in a magnetic field and you make a boost, then you might see in another frame that there's an electric field and a magnetic field. There you're transforming the fields too. But what I'm saying is that if that's a magnetization, you don't do that. That's all I'm saying. So stick with the example of the Earth, and you will be fine. So there will be, like in the notes, there will be some comment about this, and I guess some references if you are like really into defining all types of Lorentz transformations. It's not a great thing, but okay. So for our purposes, this B breaks Lorentz symmetry. Okay, so I've said all this. Actually, how am I doing on time?
You have 5 minutes.
5-10 minutes? Okay. 5-10, okay. Okay, this I'm gonna keep. And I'm gonna, so if you have any questions, this is a good time to ask them. Yeah. Yeah. Yeah, so here, I mean, you could say that, you could project your Hamiltonian to the Vial cones, and you would have chiral symmetry, and in this subspace, they would not be coupled. Yeah. So I guess that's the answer. Okay, so okay, we'll be talking about, yeah. That's what I mean. That's observer, yeah.
The transformation that would actually, I mean, if you really just explicitly wrote it down.
Yeah, you don't transform this vector.
You just by hand say.
Exactly, yeah, because it's a property of my vacuum. Yeah. That's kind of the, usually, particle and observer are the same thing because you transform everything. But here, I want to make a difference. Yeah, it's kind of a bit, that's not typically in textbooks because you always, yeah. So, but I guess that's the point of these, that's a side comment. Like, this is the point of these lectures. I'm using many things that are actually in textbooks, and I think it's better just to, explain some stuff that are not, that is, you cannot find really that well in textbooks. Especially like Lorentz breaking theories are typically not treated, but they're really important to us. So, right, okay, so coupling to an electromagnetic field. How do you do this? Well, minimal substitution. K goes to E times A. A is the vector potential. In general, you would do this. And you can define your field strength. I'm not sure if I'm going to use it, but just to remind you. And the components of this guy would be the electric field, the magnetic field, and so on. So I'm saying this because now I can add this substitution here, this minimal substitution here, and I can define an action that depends on A. By the way, Feynman wrote this as K slash. So sometimes I'm going to use this. It just means that gamma mu is dotted with whatever vector. So in this notation, K slash B slash gamma 5. You can see the use of that. And now E is just, like the coupling to the electromagnetic field is just A slash. Right? Okay. So so the reason I do this, besides I'm going to calculate some observables later, is that note that these two things are not very different. One is coupling to, if I write this term in all its full glory, it will look like this. And this guy, so this is this, and this guy is something like this. So they're not that different. It's just the gamma 5, right? It's just that this B distinguishes chiralities. That's why all the signs are different. This sign is different in the different chiralities, and this sign is different. That's what the gamma 5 does for you. It distinguishes chiralities. So it's really tempting to define something that's called a chiral gauge field, which is A5. And even though you might be tempted to do this, there are very important differences why this A5 is not the same as the B. I mean the A5 that the high energy physicist would use. The reason is that A5 is a gauge field, while B mu is an observable. It's actually, as I said, if you think about the spatial components and magnetization, I can measure magnetization. Well, this guy, I can do gauge transformations. I can do many things to make it ambiguous. So, and that has very important consequences. In particular, if you want me to name one, is that there's no chiral magnetic effect, and we will see that at some point. And so if you treat this like an A5, then the temporal component of this is actually a chemical potential rather than a parameter in a Hamiltonian. And this has physical consequences. But just to say, just a word of warning, they look similar, but you have to always remember that one is parameters in your Hamiltonian, and the other one is coupling to some external field. And this will make a difference. Okay, so I think I'll say this and then I'll stop. So generalizations of Lorentz breaking theories. I need a G here somehow. Lorentz generalizations? No. Okay. So I'll think about it. So of course, this is not the only term I can write that breaks Lorentz invariance. There are many, and people have thought about many of them. One very simple one is, okay, you know what? I have Fermi velocities in my theory. Why not include them? So I can write a matrix that I don't know really why, but I'm going to call M, big M. I could call it big V or something, but this. So this M, if it's only incorporating Fermi velocities, it would be a diagonal. So M is like diagonal of 1 minus Vx minus Vy minus Vz. And so that when I do this multiplication out, it will correctly add a Vx to the K and so on. But this is really not a big deal because I can kind of nearly always rescale the Ks to incorporate the V's when I'm calculating stuff. So it's not a big deal. Actually, we'll see an example of that. And in fact, chirality is like if you want to know if you set M to 0 and so on, and you want to ask what's the chirality, you just have to calculate the sign of the determinant of M, and then this would give you the chirality of. So basically, what before was this minus and this plus. But in fact, there are other things I can do. For example, I can promote this M. So as I said, we're always working with a 4x4 Hamiltonian. So how many 4x4 matrices are? So there are 16, right? So I'm going to promote M to, I'm going to call it M twiddle, to something that looks like this. Like this is the most general mass term you can write that breaks Lorentz invariance in the way I described before. Actually, I always forget. Stupid. M5, comma 5 plus MM. Actually, so this object here. Okay, so this is the way one constructs all matrices in all 4x4 matrices. So you already know 5. There's gamma 0, 3 gamma i's, and gamma 5, right? So these are 5. So M, and the identity, of course. So the identity, I use the matrix, the mass, which we already had. I can also write a M5 mass, which is gamma 5. Then gamma 0 and gamma I can write another vector. But note that this vector I can absorb in a redefinition of the fields. If I write so this guy is kind of irrelevant because I can do this. E, A mu, X mu. And if you plug this in here, you can absorb this term in the definition of the field, so this is not really important. Another way of seeing this is that if I'm going to couple it to a gauge field, I can reabsorb it in the gauge. This one is the one we already have. So these are another 4. So we had, how many? We had 3, 4, 5, 6. We had 6, 4, and now we have this guy, which is some second-rank tensor contracted with the sigma mu nu, which I defined as I over 2 commutator of gamma mu, gamma nu. So this obviously vanishes when mu is equal to nu, so there are 6 independent, and it's antisymmetric, so there are 6 independent matrices, and there are 16. Okay, so 16 matrices. So you can do a similar game with writing here a very general, let's say G mu nu, and like write other generalizations of the gamma matrices in a similar way. I'm not going to talk about any of that because this is already going to give a lot of like nice properties. But just keep in mind that in fact, terms like this, if you diagonalize the Hamiltonian, just you add them here, you will see that they lead to nodal lines, for example. So nodal lines can also be incorporated into this formalism by adding terms like this. And actually, there's a paper by Burkov and so on that they do this. I mean, they never call it Lorentz breaking and so on, but they write this kind of general mass term, and they start playing around with how many phases do I have, just the same as I did, but with kind of more general mass term. So yeah, so this is kind of, so if you dig deep enough, you will find that people have studied these guys, but we will focus on this. Okay, I think I'm going to stop here and take any questions, and thank you. Right. Yeah. No. No. So you would make the mass change sign. Let's say, like if I put B0 and B0, like leave all the B's to 0. And now I have a Dirac Hamiltonian. And if I change the mass, the sign of the mass of a Dirac Hamiltonian, I'm going to find a localized state. So it's like in this picture, it's always localized state at the interface, obviously. Now in this picture, the TI is always defined in terms of a relative sign change of the mass. So I would have to promote this mass term to be space dependent, and then I could describe a TI. Yeah, and in fact, you can describe with this theory, you can describe many like interfaces of vials with TIs, but just letting everything depend on position on position essentially. You go to real space, whatever you go to have to real space, but other than that, you just make the B space dependent, the M space dependent, and you see how they interplay, and you can I can tell you more about that.